Tonight's file begins with a visitor that didn't belong here, not bound to the sun, not from our neighborhood. We noticed it late, watched it briefly, and then it slipped away, forever out of reach. This is Oumuamua, the first confirmed interstellar object we ever observed up close. The data is real, the window was short, and the physics still sparks arguments. In this episode, we separate what was measured from what people wish it meant, and we ask a simple question. If the next one arrives, will we be ready to test it properly?
Before we touch any theories, we lock in the rule of space case files. Observation first, interpretation second, confidence only when the evidence earns it. So what do we actually know about Oumuamua? We know it was real, we know it was fast, and we know it was not gravitationally tied to the sun the way ordinary asteroids and comets are. Most objects in our solar system travel on paths that are bound, ellipses. They loop around the sun again and again. This visitor did not. Its path was hyperbolic. It came in from the dark between stars, curved around the sun once, and headed back out on a trajectory that will never return. That single geometric fact, unbound motion, is why it matters. Not because it was mysterious, because it was the first time we could study, in real time, a solid object from another star system passing through ours. Now here is the first limitation that shapes everything. We detected it late. By the time telescopes were pointed, it was already on its way out, getting fainter by the day. So instead of weeks or months of rich data, we got a short window, enough to measure a path, track brightness, and take limited spectra. Not enough to settle every argument people wanted to settle. In other words, this case is not a puzzle because the universe was teasing us. It's a puzzle because we missed the early frames. Let's talk about how this kind of object is even found. Modern sky surveys take repeated images of the same regions and look for anything that moves against the star background. Stars stay fixed. A nearby object shifts position. The software flags it. Humans verify it. Then, the orbit is calculated from multiple nights of measurements. At first, an interstellar visitor can look like a normal asteroid, a dot that moves, nothing cinematic. The interstellar part shows up only after we fit the orbit and realize the curve is too open to be bound. And that realization comes after the object is already fading, because the surveys usually spot it after it has passed its brightest point. So the timeline often looks like this: detection, confirmation, orbit feed, alert to the community, rapid follow-up, and then a race against distance. That is why Oumuamua became a lesson as much as a discovery. It showed us that the next visitor might be found late too, unless we build systems that catch them earlier and coordinate faster. Now, what do astronomers actually measure? They measure light and position. Position over time gives an orbit, where it is, where it was, where it will go. Light over time gives a light curve, how the brightness changes as the object rotates. Light split by wavelength gives a spectrum or color, hints about surface properties and composition. None of those measurements is a close-up photograph. So when you hear a confident statement like, "It was shaped like X," your first question should be, how many different shapes would match the same light curve? Because the answer is more than one. Let's start with motion. The trajectory was measured precisely enough to say, this object is leaving the solar system. That's the interstellar part. But motion also tells you something else. How close it passed the sun, how fast it was moving, and how much time you have before it becomes too faint to track. And with Oumuamua, that clock was brutal. Imagine trying to study a bird that appears for a few seconds at the edge of binocular range, then flies straight away from you. You can confirm it exists, you can estimate speed and direction, You might catch a few seconds of wing pattern, but you cannot measure every feather. That is the data reality we're dealing with. Now, brightness. Oumuamua's brightness changed strongly as it rotated. That's one of the most repeated facts, and it's also one of the most misunderstood. A large swing in brightness can mean the object is elongated. It can mean it has strong contrast, bright areas and dark areas. It can mean the rotation is tumbling, not smoothly spinning like a balanced top. And it can mean a mix of these things. Here is the careful version. The light curve suggested an unusual shape or surface behavior, and likely a complex rotation state. Here is the careless version. We know it was a cigar, or we know it was a pancake. Those are model-friendly metaphors, not photographs. Why do people jump to metaphors? Because the human brain hates uncertainty. It wants a picture. But astronomy often works in silhouettes. You learn about shape from how light rises and falls, from how fast it repeats, and from how stable that pattern remains. If the pattern is irregular, you infer tumbling. If the repeats drift, you infer complex rotation. Another detail people miss, the surface reflectivity, what astronomers call albedo, matters a lot. A small bright object can look as bright as a larger dark object, so size estimates often come as ranges, tied to assumptions about reflectivity. That is not a weakness of astronomy, it's an honest statement of what the data can support. So if you see a single number for Oumuamua size, treat it like a headline, not a measurement. The safer language is, it was likely on the scale of hundreds of meters, give or take, depending on reflectivity and shape assumptions. Now, color and surface. Observations suggested a surface that was not wildly exotic in color, more consistent with a natural object whose outer layer had been processed by long exposure to space radiation. Interstellar space is a harsh environment. Cosmic rays and micrometeoroids can alter surfaces over long timescales, darkening or reddening them. So, a weathered surface is not surprising. But again, this does not tell us the interior. It tells us about the skin. And when you only see the skin, the honest move is to list plausible classes, not to declare identity. At this point, the public story usually takes over. Interstellar origin? Check. Odd light curve? Check. Short observation window? Check. Then the internet adds the last ingredient, certainty. And certainty is exactly what this case does not provide. So let's mark what is solid. Solid number 1. The orbit was unbound, interstellar. Solid number 2. The light curve indicated strong variability and likely non-simple rotation. Solid number 3. The spectrum and colors did not provide any obvious signature of an artificial object. Everything beyond that lives in the space of models. Now we arrive at the phrase that gives this episode its subtitle, Weird Physics. Some analysis reported that Oumuamua's motion included a small additional component, an acceleration that didn't match pure gravity alone. If that sounds dramatic, slow down. Non-gravitational acceleration is common in comets. Outgassing, ice turning into gas, can create a tiny thrust. It's subtle, but over time it becomes measurable. That is normal physics. So why did it feel weird here? Because observers did not see the usual visual companions, a clear coma, a dust tail, a messy halo around the nucleus. That absence doesn't prove there was no outgassing. It means if outgassing happened, it was either weak or in a form that was hard to detect, or the data wasn't sufficient to catch it. And there is a second layer. Orbit fitting is a model. when you have limited measurements, small systematics, tiny biases in astrometry, small changes in how you treat uncertainties, can shift the inferred extra push. That does not mean anyone faked anything. It means the result can be sensitive. So in this series, we treat the claim properly, not as a verdict, but as a testable question. If there was an extra push, what mechanism could produce it? If there was no extra push, why did the field appear to need one? And what observations would separate those cases? This is also where interstellar objects become more than curiosities. Because if you can measure how they accelerate, how they spin, and how they shed material, if they do, then you can learn about formation in other star systems. Not aliens, not mystery for mystery's sake, real astrophysics. One more context point. Oumuamua was the first, not the last. A later interstellar visitor behaved like a classic comet, active with visible signs of gas and dust. And now, with 3i Atlas, we have another interstellar visitor to compare against Oumuamua's quieter profile. We'll come back to 3i Atlas in part 3, because it helps us ask, was Oumuamua an outlier, or did we simply miss the evidence? But for part 1, our mission is simpler. Establish the chain of observations and the chain of limitations. We saw a fast, unbound object. We measured its path precisely enough to confirm it came from beyond the solar system. We tracked its brightness and inferred a strange, likely tumbling rotation with strong variability. We took limited color and spectral data consistent with a natural, weathered surface. And then it was gone. No second pass. No let's send a probe. No extra month of tracking to reduce uncertainties. Just a file folder with real numbers and a lot of blank space around them. So here's the summary of part 1 in one sentence. Oumuamua was a confirmed interstellar object observed briefly through light and motion. Enough to prove its origin, not enough to settle every property people wanted to name. In part 2, we'll zoom in on the disputed physics. What extra acceleration could mean, what could mimic it, and what would have counted as decisive evidence if the data window had been longer. There's also the matter of the name, because names can sneak a story into the data. Oumuamua is a Hawaiian word often translated as something like scout or messenger arriving first. It's poetic and it's fine, as long as you remember the poetry is not evidence. In the technical catalogs, it was labeled as the first interstellar object of its kind, 1I. That label is just bookkeeping. It doesn't imply intelligence. It implies order of discovery. Now, why do astronomers expect interstellar objects at all? Because planet formation is messy. Young star systems fling material around. Giant planets scatter smaller bodies. Close stellar encounters can eject debris. Over billions of years, the galaxy should be filled with small wanderers. Most are tiny and dark, and space is huge, so we rarely notice them. Oumuamua didn't prove interstellar objects exist. The physics already suggested they should. What it proved is that our instruments are finally sensitive enough to catch one when the timing is just right. And timing really is everything. Objects like this are easiest to detect when they are close, because brightness falls off quickly with distance. But close can be brief when the object is moving fast. The moment you identify it as unusual, interstellar, the moment you want more data, is usually the moment the data becomes harder to get. Orbit fitting is another place where the public story often skips the hard part. An orbit is not guessed from one snapshot. It is solved from many measurements of position, each with its own uncertainty. Small uncertainties matter when you extrapolate backward to where did it come from, and forward to where is it going. For Oumuamua, the solution was clear enough to classify it as unbound, but details like the exact incoming direction, the precise speed at infinity, and the subtle residuals that hint at an extra force, that's where debates live. Now let's unpack the light curve a bit more, because this is the most visually intuitive data we have. If a rotating object is roughly spherical and evenly colored, its brightness doesn't change much as it spins. If it's elongated, like a stretched rock, or has highly reflective faces, then the brightness can swing dramatically as different cross-sections face the telescope. And if it is tumbling, rotating around more than one axis, then the pattern becomes complex. It may repeat imperfectly, it may drift, it may look quasi-periodic. That matters because a lot of shape certainty on the internet comes from treating the light curve as if it came from a simple stable spin. But if the rotation is non-simple, then multiple shapes, multiple surface patterns, and multiple spin states can fit. The more complex the motion, the wider the family of solutions. There is also geometry, phase angle, the angle between the sun, the object, and the observer. As that angle changes, the apparent brightness changes even for the same object, because you are seeing it under different lighting. Think of how a rough rock looks different at noon than at sunset. So the light curve is not just shape. It's shape plus rotation plus lighting plus surface texture. This is why the most responsible summaries use phrases like consistent with, suggestive of, and best fit under these assumptions. Those phrases are not hedging. They are the scientific equivalent of showing your work. Now, what about direct signs of comet-like behavior? The classic signature is a coma, a diffuse cloud of gas and dust around the nucleus, sometimes with a tail. That's visible because sunlight scatters off the dust, and because certain gases emit at characteristic wavelengths. With Oumuamua, observers did not see an obvious coma in the imaging that was taken. That is one reason the outgassing explanation became contentious. But absence of an obvious coma is not the same as proof of absence. A weak coma might be below detectability. A gas-dominated outflow with little dust could be hard to see. A jet pointed in an unlucky direction could produce thrust with minimal visible spread. And again, limited data means limited sensitivity. There were also attempts to detect Oumuamua in other ways, outside the visible light window. Infrared observations can constrain size because warm objects glow in infrared, depending on their surface properties. If you don't detect it, you can still say, it can't be both very large and very dark, because then it would have shown up. These constraints feed back into the size and albedo uncertainty we talked about earlier. They don't solve the case, they tighten the fence around the solution space. And here's a subtle point. Every time you tighten the fence, the storytelling options shrink. That is why careful work can feel less exciting. It removes the wild possibilities first. That's not boring, that's progress. So why does this still feel unresolved? Because the remaining possibilities still span very different pictures. A natural rock with an unusual shape is one picture. A volatile rich body venting invisibly is another. A fragile, fluffy aggregate pushed by sunlight is another. And yes, people propose artificial explanations too, but those live on the far end of the plausibility scale without direct evidence. The important thing is that we can describe for each picture what it would predict. Would it produce detectable gas? Would it change spin rate? Would it brighten in certain wavelengths? Would it show a tail? Would its acceleration vary with distance from the sun in a specific way? Those are not philosophical questions, they are observational tests. And that sets up the purpose of this whole episode. Oumuamua is not the kind of mystery you solve by arguing louder. It's the kind you solve by designing the next observation campaign, so the next interstellar visitor doesn't slip through our fingers with only a partial file. That is why we're including 3i Atlas in this episode at all. It is a living comparison case, an interstellar visitor where activity and follow-up can be measured more directly. And it's why we'll mention Apophis later as a near-Earth laboratory. Not interstellar, but a rare close pass that lets us test how small bodies respond to heating and gravity, the same physical processes that complicate these cases. One last reality check before we close part 1. Even if Oumuamua had been completely ordinary, it would still be historic. Interstellar objects are rare to catch, and the first one will always carry noise in its record simply because our methods were not optimized yet. So when you hear weird physics, try hearing it as first contact with a new dataset class. The weirdness may belong to the object, or it may belong to our sampling. Either way, the only honest next step is to quantify it. One more misconception to clear up. Interstellar does not mean we know exactly which star it came from. In principle, you can trace an incoming direction, but stars move. The object may have wandered for a very long time, and small uncertainties grow when you rewind the clock. So the safest statement is simply, it came from outside the solar system. Its birthplace remains unknown. It's also worth saying out loud what everyone secretly wants, a close-up. The reason these stories explode is simple. If you could zoom in, you wouldn't need metaphors, you'd have an image. But the solar system is not a studio. When a fast object is already outbound, the travel time for any spacecraft concept becomes the enemy. Intercept missions require years of planning, a launch window, and enormous delta V. By the time the world knew Oumuamua was special, the world was already late. So the real lesson of part 1 is operational. Interstellar visitors force us to act on incomplete information, quickly. You don't get to wait for perfect data. You get to choose. Do we spend scarce telescope time now, or do we let it go because we're not sure it's worth it? With Oumuamua, the answer was spend it, and we learned exactly how tight the timeline can be. This is why the next generation of surveys matters so much. Better surveys mean earlier detection. Earlier detection means the object is brighter, closer, and still approaching, so you can measure how it changes as it warms under sunlight, not just how it fades as it leaves. That single shift, catching an object before perihelion instead of after, can multiply the science return. And coordination matters just as much as hardware. An interstellar alert has to trigger a choreography: imaging, spectroscopy, polarimetry if possible, infrared attempts, and continuous astrometry to refine the orbit. If the object shows activity, you want to watch how that activity turns on and off. If it doesn't, you want the tightest possible limits on gas and dust, because non-detection is still data. This brings us back to the core promise of space case files. We don't treat mysteries as vibes. We treat them as checklists. What was measured? What was not measured? What would we measure next time? And which explanations survive the checks? So as you listen to this part, keep one mental image: a file folder labeled Oumuamua. Inside, a clean orbit solution, a jagged light curve, limited color data, and a set of competing interpretations. The folder is real. The blank pages are real too. In part 2, we'll fill those blank pages the only honest way, by testing mechanisms, not by choosing a favorite story. Part 2 is where the phrase weird physics enters the room. but we're going to treat it like a lab problem, not a headline. When astronomers say non-gravitational acceleration, they mean the object's motion shows a tiny extra component that isn't explained by gravity alone. In the solar system, that is not exotic. Comets do it all the time. Ice warms, turns to gas, and the escaping gas acts like a gentle thruster. So the correct first reaction is not aliens. The correct first reaction is, if there is an extra push, what natural mechanism could produce it? The reason Oumuamua caused debate is the combination of two claims: a small extra acceleration and a lack of obvious comet-like dust or coma in the images available. That combination creates tension, and tension is where theories multiply. Our job is to sort those theories by testability and plausibility. We'll do it in three baskets: ordinary physics, rare but natural physics, and the speculative basket that requires extra assumptions. First, a crucial caution: orbit fits are models. They're built from measurements of position over time, each with uncertainty. If your measurement errors have small biases, systematic offsets, your model can interpret that as a physical effect. This does not mean the effect is fake. It means the effect must be robust to changes in assumptions. In practice, researchers test this by refitting the orbit under different weighting schemes, checking residuals, and seeing whether the extra push remains consistent. So whenever you hear a single definitive sentence like "Oumuamua accelerated," mentally append, under these assumptions, within these uncertainties, given this dataset. That's not skepticism for its own sake. That is how you keep yourself from building a story on a fragile parameter. Now, with that caution in place, we can explore mechanisms. Because even if the effect is small and uncertain, asking what would cause it teaches us what to look for next time. Basket 1. Ordinary physics. The most straightforward mechanism is outgassing, volatile material warming and escaping as gas. If a jet of gas exits one side, the object experiences a small thrust in the opposite direction. Why does this feel incompatible with the observations? Because we didn't see a clear coma or dust tail. But ordinary physics has several ways to hide. If the outflow is gas-dominated with very little dust, the coma can be faint. If the jet is narrow and aligned in a way that doesn't spread much dust into our line of sight, it can be missed. If the total production rate is low, it can be below detection limits. And remember, our observation window was short, and the object was already fading. Non-detection is not a slam dunk, it is a constraint. It says, if gas exists, it must be below this level, or if dust exists, it must be below this level. So the honest statement is, outgassing is plausible in principle, but the lack of visible coma puts pressure on the simplest comet-like picture. Here's what outgassing would predict. This is important. If an object is outgassing, you might expect 1. A measurable change in rotation state over time, because jets can produce torque. 2. Specific gas emission lines in spectra if the gas is detectable. 3. A relationship between acceleration and distance from the Sun that matches how heating turns volatiles on and off. But with Oumuamua, we lacked enough continuous, high-quality monitoring to nail those predictions down. We had snapshots, not a complete time series. So the case becomes, could outgassing produce the reported acceleration while staying under detection thresholds for dust and gas? Some argue yes, with the right conditions. Others argue it strains credibility. That is how real scientific disagreements look. Not this is impossible, but this requires parameters that may or may not be realistic. Basket 2. Rare but natural physics. This is where ideas get creative without leaving reality. One family of ideas says, maybe the acceleration wasn't driven by gas jets at all, but by sunlight. Sunlight carries momentum. When photons hit a surface and are absorbed or reflected, they transfer a tiny push. For most asteroids, this is negligible, but for an object with a very high area-to-mass ratio, something thin, porous, or fluffy, the push can become measurable. This is a real physical effect. The question is whether a natural object can have the required structure and survive the stresses of interstellar travel and the solar flyby. If an object were extremely porous, think a fractal aggregate or a loosely bound puff, it could have a large surface area compared to its mass. That could amplify radiation pressure. But such objects might also be fragile, and the environment is not gentle. So again, plausible mechanism, challenging parameters. Another rare but natural idea focuses on phase changes that are hard to see. Not all volatiles produce the same kind of coma. Some materials could sublimate without producing much dust. Some could release molecules that are difficult to detect at the wavelengths observed. There is also the possibility that the surface was crusted, sealed, after long interstellar exposure, with pockets of volatile material beneath. A sealed surface can suppress a classic dusty coma, while still allowing some gas to escape through cracks or vents. And then there is geometry. If the acceleration depends on which side is heated, then a tumbling object would modulate the effect in a complex way. That could make it harder to fit with a simple model, and it could create apparent inconsistencies depending on sampling. In other words, the more complex the object's rotation and surface, the more you should expect simple comet predictions to fail, even if the underlying mechanism is still natural. Now we reach the speculative basket. This is where public attention goes, but in this series we handle it in a controlled way. Speculative explanations require extra assumptions that are not demanded by the data. They are not automatically wrong, they are simply lower priority until stronger evidence appears. An artificial object hypothesis is the most famous example. If you assume an object is engineered, you can explain many things. Thin shapes, high area-to-mass ratios, unusual acceleration. But the question is not, can you imagine a design? The question is, what unique signature would separate design from nature? Without a unique signature, communication, maneuvering inconsistent with passive forces, structure visible in high-resolution imaging, this basket remains speculative. And in the Oumuamua case, we did not have those signatures. So the correct treatment is acknowledge the idea exists, then return to testable physics. Here is a useful way to rank hypotheses. Ask, how many new entities do you need to add? Natural outguessing needs none. Comets already exist. Radiation pressure needs none. Photons exist. It only needs an unusual structure. An engineered artifact needs a whole extra chain, a builder, a launch, a purpose, and the reason it behaves exactly like a passive object while passing through our solar system. That doesn't make it impossible, it makes it expensive in assumptions. And in science, the more assumptions you need, the more evidence you owe. Now, let's go back to the heart of the controversy. Could the extra push be an illusion? Sometimes, what looks like a non-gravitational term can arise from subtle observational limitations. If astrometric points are sparse, if some measurements have larger uncertainties than reported, if the object's photocenter shifts as it tumbles, you can get residual patterns that mimic a force. That doesn't settle the question either way. It tells you what to watch next time. Dense astrometry, consistent calibration, and careful modeling of the light distribution. The most important thing to understand about this debate is that it is not unique to Oumuamua. It's a classic problem in small body dynamics. Tiny forces matter when you integrate motion over long arcs, and small uncertainties can masquerade as physics. So the weirdness is a signal about our measurement frontier. We are trying to infer subtle effects from limited, fading data on an object that was never meant to be easy to observe. If you want a mental model, imagine a detective reconstructing a car crash from 5 blurry photos taken after the cars were already towed away. You can still learn something, but you must be honest about what you cannot learn. Now, here's a key question. If the acceleration was real, what direction was it in? Because different mechanisms push in different ways. Outgassing can push in directions tied to jets and rotation. Radiation pressure pushes away from the sun, tied to surface area and reflectivity. So the vector of the acceleration, its direction, matters as much as its magnitude. And this is where we hit the wall again. The data window limits how tightly you can constrain direction and variation over time. So rather than pretending we can solve it, we do the productive thing. We list the decisive observations we wish we had. 1. Early detection, so we can track the object while it is still inbound and bright. 2. Continuous spectroscopy, so we can detect faint gas signatures or place strong upper limits. 3. Deep imaging with long exposures to search for any coma or dust tail at extremely low levels. 4. Thermal infrared observations to better constrain size and surface properties. 5. A dense astrometric campaign to model any non-gravitational acceleration with confidence. Now we ask, do we have a case where some of these boxes are easier to check? Yes, and that brings us to the second interstellar visitor we include in the title, 3I Atlas. We are not claiming 3I Atlas is the same as Oumuamua. We are using it as a contrast case, an interstellar visitor that shows more classic, measurable behavior, so we can compare what active looks like versus what quiet looks like. And when we do that, we can ask a sharper question. Was Oumuamua truly strange, or was it simply observed under conditions that made it look strange? Before we leave part 2, there's one more layer, human psychology. Because cases like this don't exist in a vacuum. They exist in a culture that loves mystery. When the data is thin, narratives rush in to fill the gap. That's normal. The brain wants closure. It wants a clean label. But the scientific move is to hold the uncertainty and keep the hypothesis space organized. So here's the simple ranking logic for this case, based on evidence cost. Low-cost hypothesis first, high-cost hypothesis last. Natural mechanisms that are known to exist come before mechanisms that require new kinds of objects. Mechanisms that predict testable signatures come before mechanisms that can explain anything after the fact. This is not about being conservative, it's about being falsifiable. If an idea cannot be cornered by data, it does not belong at the top of the list. And this is why the phrase weird physics can be misleading. What's weird might not be the object. What's weird might be that we're trying to do high-precision inference with a short, fading track. So let's close part 2 with a disciplined summary. 1. A small non-gravitational acceleration was reported in some analysis, and it became the centerpiece of debate. 2. Outguessing is the most straightforward natural mechanism, but the lack of an obvious comma makes the simplest version uncomfortable. 3. Radiation pressure and unusual structures offer another natural path, but they require parameters that may be rare or fragile. 4. Purely observational or modeling effects could mimic a small acceleration, especially with sparse, noisy data. 5. Speculative explanations exist, but they do not have unique signatures in this dataset, so they remain low priority. If you take nothing else from this part, take this. The case is not solved, and it's not unsolved in a dramatic way. It is constrained, it is boxed in, and what remains is a manageable set of testable mechanisms for the next visitor. And that sets up part 3, because part 3 is where we stop staring at Oumuamua's missing pages and start asking, what can we do differently next time? We'll use 3i Atlas as the active contrast case, and we'll point to Apophis 2029 as a near-Earth laboratory for small body physics. So the next time an interstellar object arrives, our case file won't be half empty. There's a phrase that belongs here. Extraordinary claims require extraordinary evidence. But in practice, what it means is simpler. Extra assumptions require extra data. If you assume outguessing, you should look for gas signatures and spin changes. If you assume radiation pressure, you should look for a correlation with solar distance and surface properties. If you assume an engineered object, you should look for behavior that cannot be produced by passive forces. In this dataset, we mostly do not have the discriminating measurements. So the rational stance is not cynicism, it's planning. Plan the next observation strategy so that the next object gives you discriminating measurements by default. That planning is already happening in astronomy. Surveys are improving, coordination is improving, and the community has a clear incentive now. Interstellar objects are not theoretical anymore, they are real targets. So when you hear weird physics, translate it into we have a new category of visitor and we are building the playbook. And this is why part 3 won't be a list of guesses. It will be a checklist of measurements. Because checklists are how mysteries turn into understanding. We'll talk about what 3i Atlas can reveal that Oumuamua couldn't. Direct activity, better constraints on composition, and a richer light curve. We'll talk about the specific tests that separate gas thrust from sunlight push from model artifact. And then we'll zoom closer to home, Apophis 2029. Not because it's interstellar, but because it is a rare natural experiment. When an object passes close to Earth, gravity can torque it, reshape regolith, and alter rotation. If we can measure those changes well, we improve the same physics toolset we need for interpreting distant visitors. So part 2 ends here. The debate is real, the uncertainty is real, and the productive next step is also real. Part 3 is where we build the future case file. Next, 3i Atlas, the active interstellar visitor, and the tests we can run while it's still in range. Then, Apophis 2029, the near-Earth laboratory that will help us read small body physics with less guesswork. Because the goal of space case files is not to collect mysteries, it's to shrink them. Part 3 is the payoff. Not a new theory, an actual plan, because Oumuamua taught us a painful lesson. One short window creates years of arguments. So the only way forward is to build a playbook for the next visitor. What we measure first, what we measure continuously, and what we never skip. This is where 3i Atlas matters. in the title, it's not there as clickbait. It's there because it gives us a contrast case, an interstellar visitor where the signals we want, activity, composition clues, and dynamic behavior can be measured more directly. So think of part 3 as a field manual. If an interstellar object shows up, how do we stop it from becoming another signal that never came back? We start with the biggest upgrade: earlier detection and rapid coordination. Earlier detection changes everything. If you catch an object while it's still inbound, you can measure how it evolves as sunlight increases. That matters because many mechanisms, outgassing, thermofracturing, radiation pressure effects, scale with solar heating. With Oumuamua, much of the observation happened after the peak brightness, when it was already leaving. That's like trying to diagnose a fever after the patient already recovered. You can still learn something, but you've lost the strongest signal. So the first item in the playbook is simple. The moment a candidate orbit looks unbound, you trigger a maximum data response. That response is not one telescope, it's many, because different instruments cover different wavelengths, and different sites cover different times. And this is exactly why a case like 3i Atlas matters. It pushes the community to practice that choreography. Now let's talk about what we actually want to measure, in order. Number 1. High cadence astrometry. Position measurements frequently with good calibration. Because if there is any non-gravitational acceleration, you want to detect it early, model it, and see how it changes with distance from the Sun. Number 2. Deep imaging for coma and dust. Not one photo, a repeated program with long exposures and consistent processing. Because a faint coma can be invisible in a single frame, but obvious in stacked images or by comparing nights. Number 3. Spectroscopy. If gas is present, you want molecular signatures. If it isn't, you want strong upper limits. Either way, spectroscopy turns maybe into bounded. Number 4. Thermal infrared, if possible. This helps constrain size and surface properties in a way visible light can't. And number 5. Rotation monitoring. Light curves over time. Because if the object is active, jets can change spin. If it's pushed by radiation pressure, the torque signature can look different. Now place 3i Atlas into that checklist. An active interstellar object gives you built-in tests. Activity means there is material leaving the surface. That material can be measured. It can be compared. It can be tracked as it turns on and off. This is the key difference from Oumuamua. With Oumuamua, much of the debate was acceleration without coma. With an active object, you can say, here is the coma level, here are the gas lines, here is the dust behavior, and here is how the dynamics respond. Even if 3i Atlas turns out to be completely ordinary for a comet, that is still valuable, because it creates a baseline, what a normal interstellar comet looks like in our instruments. And once you have a baseline, outliers become easier to identify without drama. So the role of 3i Atlas in this episode is not mystery, it's calibration. Here's a practical way to frame it. We can ask 3 questions and let the data answer them. Question 1. Does the object show measurable outgassing? If yes, we can estimate thrust and see whether it matches any non-gravitational acceleration inferred from the orbit. If no, we put strong limits on outflow and move to other mechanisms. Question 2. Does the activity change with solar distance in a predictable way? If it turns on sharply near a certain distance, that hints at specific volatiles. If it ramps smoothly, that hints at different thermal behavior. Question 3. Does rotation change over time? If jets are producing torque, you might see the period drift or the tumbling state evolve. If nothing changes, that also tells you something about how symmetric the outflow is or how weak it is. These are the kinds of measurements that would have made the Oumuamua argument space smaller. And they are the kinds of measurements we can aim for with 3i Atlas and future visitors. Now let's connect this back to the weird physics question in a very specific way. If an object accelerates away from the Sun in a way that matches radiation pressure, that suggests a high area-to-mass ratio. In that case, you want to constrain size and mass proxies, infrared limits, brightness behavior, and any evidence of fragmentation. If an object accelerates in a way that matches outgassing, you want gas detections and you want a correlation with solar heating. You also want to see whether activity is directional and whether it creates torque. If an object shows an apparent acceleration that disappears under better astrometry, then you've learned the hard lesson. You need dense, high-quality positional data before you build exotic models. That lesson alone is worth an episode because it prevents the next file from becoming a meme. So part 3 is not about which explanation wins. It's about the measurements that make explanations compete fairly. Let's zoom out for 1 minute and be honest about rarity. Interstellar objects are not common in our telescopes. Space is too big, and most of these bodies are too small and too dark. We catch the rare ones that pass close enough and reflect enough light, and often we catch them late. That is why the next one matters so much. Each new interstellar visitor is not just another mystery, it's another data point in a tiny sample size. With a sample size of 1, everything looks exceptional. With a sample size of 10, patterns emerge. So the real goal is to build a catalog, not a legend. A catalog is what allows you to say, this behavior is normal, this behavior is rare, and this behavior is truly anomalous. And this is why the title includes both Oumuamua and 3i Atlas. 2 interstellar visitors already tell you more than 1 ever could. Now, where does Apophis 2029 fit in? Apophis is not interstellar, it's a near-Earth asteroid. So why mention it in an interstellar episode at all? Because it gives us a rare, controlled experiment in small body physics. When Apophis passes close to Earth, gravity can alter its rotation, shift surface material, and potentially change how it reflects light. And unlike an interstellar visitor, Apophis will be close enough for detailed radar and optical observations that can directly test models. In other words, Apophis is a calibration event for the same toolbox: orbit modeling, rotation state, surface response to forces, and the difference between what we can infer from light curves versus what we can measure directly. So Apophis is the nearby rehearsal. Interstellar objects are the surprise performance. If we want to interpret surprises well, we practice on what we can study up close. Here's the deeper connection. A huge amount of confusion in cases like Oumuamua comes from trying to infer physical properties from limited data. Apophis gives us a chance to validate those inference methods. For example, how reliable is a shape estimate from a light curve alone? With Apophis, we can compare light curve models to radar shape models. That tells us how often our best fit is misleading. How reliable is rotation state inference? With Apophis, we can watch rotation change due to Earth's gravity and see whether our models predict the change correctly. And how do tiny forces show up in orbit feeds? Near-Earth objects are tracked with incredible precision. That's how we learn to separate real small accelerations from artifacts of measurement and modeling. All of that improves our ability to interpret a fast interstellar visitor where we will never get radar. So Apophis is not a detour, it's a training ground. Now let's make the promise concrete. If another Oumuamua arrives, what would we do differently on day 1? 1. Immediate multi-band photometry to lock down the light curve with high cadence. 2. Spectroscopy attempts early, before it fades, to search for faint gas signatures. 3. Deep coma searches with consistent pipelines, so non-detection is meaningful. 4. Infrared constraints to reduce the size albedo ambiguity. 5. A coordinated astrometric campaign to test for non-gravitational terms and map their direction and evolution. And one more. Communication. Not public hype, scientific coordination. The playbook only works if data is shared fast and follow-up observations are scheduled before the object is gone. This is why astronomy communities talk about triggered follow-up like it's a fire drill. Because for interstellar visitors, it basically is. So where do we went on Oumuamua itself? We went in a place that sounds unsatisfying, but is actually disciplined. The highest probability zone remains natural explanations consistent with small body physics. Some combination of shape, rotation, surface processing, and either weak outgassing or radiation pressure could explain much of what was reported. The key uncertainty is not, was it weird? The key uncertainty is, which mechanism dominated, and was the acceleration real and robust? And if the acceleration was real, the next visitor will let us test the competing mechanisms cleanly, if we catch it early and measure the right things. That's why I'm not giving you a dramatic verdict, because a verdict without discriminating data is just a personality test. Instead, I'm giving you the ladder, the steps that would move this from debate to measurement. Oumuamua was the first page of a new chapter. 3i Atlas is another page, and the next pages will be written by our ability to respond faster. Now, let's close the loop with the title Interstellar Visitors. That phrase matters because it reminds us these objects are not mythology, they are traffic. Rare traffic, but real. The galaxy should be full of ejected material. We are just beginning to see it because our surveys are finally wide and sensitive enough. So the long-term story here is not one weird rock. It's the beginning of a new observational field. Interstellar small bodies as samples of other planetary systems. And the best part is, the science gets easier with time. Not because objects slow down, but because our infrastructure improves. Better surveys, better alerts, better follow-up networks, and eventually, maybe even dedicated intercept missions that can respond quickly. That's not fantasy. That's the direction technology naturally moves when a target class becomes real. So if you want a takeaway that isn't just a mood, here it is. The next interstellar object will be less mysterious than the first, if we treat it like a drill, not a legend. And that brings us to the final ranking, very carefully. Rank 1. Natural small body explanations that don't require new entities. These include ordinary outgassing below detectability or radiation pressure acting on an unusually structured but still natural body. Rank 2. Rarer natural explanations that require more specific conditions. Unusual composition, extreme porosity, crusted surfaces with hidden volatiles, or complex torque behavior. These are not impossible, they're just less common. Rank 3. Speculative explanations that require extra layers. Engineered artifacts, intentional design, or purposeful behavior. In this dataset, we don't have unique signatures that force us into that category, so it stays at the bottom until evidence earns it. That is not a dismissal, it's a standard. The higher the claim, the higher the bar. And if you want to know what would raise the bar, a repeatable signature across multiple interstellar visitors, or a behavior that cannot be produced by passive forces. Until then, we stay anchored to what can be tested. So what comes next for space case files? Two directions. First, we'll follow 3i Atlas as data evolves, because active visitors allow cleaner tests. Second, we'll prepare for the Apophis 2029 event as a separate case file, because it's a rare close approach that will teach us how small bodies respond to strong gravitational encounters. That future episode will be practical. What observers expect to measure, what could change, and what it would teach us about interpreting light curves, rotation, and subtle forces. And that's the point of this whole format. We don't chase mysteries for vibes. We chase them for measurements. We keep what is solid, we label what is uncertain, and we design the next observation so uncertainty shrinks. Because when you do that, the universe doesn't become less interesting. It becomes more legible. And that's our case file for today. Oumuamua gave us a first glimpse and a lot of blank space. 3i Atlas gives us a chance to fill in those blank pages with direct measurements. And Apophis 2029 reminds us that the best way to interpret distant visitors is to practice on what we can study up close. Next time, we'll open a new file, another real observation, another testable pattern. And the same rule every time. Observation first, interpretation second, confidence only when the evidence earns it. Until then, keep looking up and keep listening.